Okay, so this is problem 2.9 out of Griffiths Electrodynamics. Before I get through and actually start solving this problem, I'd just like to ask if you wouldn't mind please liking this video and subscribing. It's a free way to support me, and it keeps me motivated to post more videos like this. So if you think you would benefit from having detailed solutions to these problems out of popular undergraduate textbooks, then I think you would benefit greatly from subscribing to my channel. Okay, let's go ahead and get into solving 2.9. Suppose the electric field in some region is found to be E equals K R cubed R hat in spherical coordinates. K is some constant. Find the charge density rho. So that's part A, is to find the charge density. And then we need to find the total charge contained in a sphere of radius r centered at the origin in two different ways. But just starting with A, we know from the book that the divergence of the electric field is equal to 1 over epsilon naught rho. This is equation 2.14 in the textbook. Rho can then be solved as epsilon naught times the divergence of E. Well, we know what E is, so now we just have to take the divergence of that in spherical coordinates. So in my edition, which I think is the 4th edition here, the 4th edition, it's section 1.71. So that's how you know what the divergence is in spherical coordinates. It's in the book. So then for us, 1 over r squared d by dr, r squared times er, E sub r, the electric field in the radial direction. There's some other terms as well, but our electric field is only dependent on E, so we don't really need to worry about that. We can just plug in E equals K R cubed into here. Obviously the K is a constant, so that can come out. So we have K over R squared. The derivative with respect to R squared times R cubed is R to the 5th. And the derivative of that will be 5K R to the 4th over R squared. And keep in mind, this is the divergence of E. We don't want to forget the epsilon naught. So then our charge density will be 5K epsilon naught, and then just R squared, since those terms cancel. Okay. So now we move on to B. So essentially we're going to have a sphere. It's not a very good sphere, of radius r, centered at the origin, and we want to find the enclosed charge. So there's a few ways you can do this. One of the equations in the book that we have is that the enclosed charge Q is equal to the volume integral of your charge density times d tau. This is your charge per volume, and this is a volume element. Okay. Essentially you're adding up all the charges. So we can just calculate this integral. It's a triple integral, but it's a pretty easy one to handle. Rho we just solved for. We know that's 5K R squared epsilon naught. And then our d tau, our volume element here, for spherical coordinates, is just R squared. I don't know if it's helpful or not to do this in different colors. I could do that though. So let's do this just so it's clear. I like color coordinating things. Times R squared sine theta dr d theta, d phi. Then our bounds of integration, we're going to go from 0 to r for the radial part, 0 to pi for the theta part, 0 to 2 pi for our phi part. So then our enclosed shards, we can factor out the 5k and the epsilon naught because those are just constants. If we do our theta and phi integral, that's one that's been done a few times I think at this point, that's just 4 pi. And then the integral from 0 to r to the 4th dr. Which, of course, then you can, that's just 1 over 5, r to the 5th. So the 5 will drop out there. And you'll have 4k pi epsilon naught r to the 5th. So that's one way to do it. The other way is using equation 2.13. That's the equation number in my book. Which basically says that 1 over epsilon naught times the enclosed charge is this closed integral, closed surfaced integral of E dot dA. So clearly you can solve for the enclosed charge. It's just epsilon times that integral. Okay, and we know what our electric field is. That's one of the things that we're given. So this will be a double integral of k r cubed, and then I guess just continuing with this color coordinating theme here, your dA is r squared sine theta d theta d phi. And once again we're integrating from 0 to pi and 0 to 2 pi for phi. So once again we can factor out some of these constants and you get k epsilon naught r to the 5th times, and basically all this stuff in purple, that just gets you 4 pi. That's a very common integral that I think we've done a few times now. So this is again just 4k epsilon naught pi r to the 5th. 4k pi epsilon naught r to the 5th. So two methods, we got the same result both ways. Hopefully that makes sense. If that did help you at all, I'd really appreciate it if you'd like the video and subscribe. Thank you.